I want to say a few words about these projects. So 200, you have to perform the Caesar cipher, and this is where you just move letters forward 1 or 2 or 3 spaces in the alphabet. And so you can just start from something like Hello World that you had here. This has data here in a data section, and this is Intel 32-bit code. So you're using registers like EAX and EBX. Then you just load this up with the length of the message, a pointer to the message. Device 1 is the output device, standard out, and the system call 4 in Intel is write. So then you call int 80 to write the data, and int 80 here with system call 1 to exit. So this will print something and exit. And we've done other projects where you've also used the read call to read data. So you know how to read in data and how to write it out. And so the only missing element for the Caesar cipher is to modify it byte by byte. And so you'll have to add a loop, and you'll have to step through the data character by character and then increment each character, moving it forward in the alphabet. And for this one, it may even be enough not to bother with this wraparound, although that's just a matter of a compare and then a conditional jump to see if it's gone above Z, and if so, go back to A. So that's the game. And so there's a couple of flags here that you find by just moving things forward. This one here, so the first one, you just have to encrypt this by moving every letter forward 3 in the alphabet. This time you're going to have to make a loop to try all 25 shift values and print them all out. This is how you crack the Caesar cipher by brute force. There are only 25 possible transformations, so you can just print out the result of transforming it in each of those ways and see which one turns into a readable string. And here's one where I've made an alternating Caesar, where you shift the first letter forward, the second letter backward, third letter forward, and fourth letter backward. So you'll have to add that to your code to decipher this one. So that's a simple manipulation and small step forward from what you've done previously in x86 machine assembly code. So let me just talk about XOR at the same time. It's very much the same thing. Here, we're going to use a different way of encrypting data. Rather than shifting it forward in the alphabet, we're going to do XOR. We talked about this before. XOR goes bit by bit. If the 2 bits are the same, they're both 0 or they're both 1, the answer is 0. If the 2 bits are different, the answer is 1. So you take a letter and you turn it into its binary representation, and now you can XOR one character with another. So if you do capital A XOR capital B, here's A and here's B. This is 65 and 66 in base 10. And so if you do the XOR, the bunch of it is 2 zeros that go to a 0. These 2 ones go to a 1. And this 0, 1 and 1, 0 both go to 1s. So you end up with 3. The number 3, which is not a printable ASCII character anymore, but it is a valid byte. And that's, by the way, very common. All right, but if you do A XOR lowercase s, that is printable, because lowercase s has some bits here set. So if you do the XOR here, you're going to get 2 1s to go into 0, 0, 1 going to 1, and a couple of 1s here, and that's going to turn into the numeral 2. So sometimes the result of XORing 2 printable characters is printable, but often it's not. Anyway, so here's an example of that program. I've got data down here, and I use the C register to keep track of a loop, and then I'm going to use loop. Loop will automatically decrement the C register and quit when it hits 0. So this is one way to save yourself a compare, to use that feature. So now it'll load the message, it'll add ECX to it, and then it's going to subtract 1 from that value, and then put the address, load AL into there. So move, I have a little trouble. Okay, the source destination. So move the EBX, right, the address of the current character, because this is going to load the current byte in AL. Notice the AL here. This is how I tell it to do calculation 1 byte at a time. Up here, I'm doing 32-bit calculations because I'm getting the 32-bit address of the pointer to the message, and then adding the offset, which is also a 32-bit value, although it started at 5 and it's counting down, and then subtracting 1 from that. because if I have a 5-character message, it goes from location 0 to 4. So I don't want to write to location 5. I made that mistake earlier. So you subtract 1. So here's the actual address of the character we're currently working on. You move it into AL, so you have the 8-bit character there. Now you can XOR it with 3 and then put it back in there, moving that 1 byte back in. And then you're ready to just move forward. And I pushed ECX and popped it, although I think that was not really necessary. But I was concerned that some operation here might affect ECX. In retrospect, I think I did not need to do that. That would be appropriate if I was trying to print something out here doing a syscall. It has to use ECX. I think this push and pop could be removed. But anyway, that's going to do the loop. That's the basic working. That shows you how to do XOR encryption, and doing the Caesar cipher is very similar. So you've got a couple of challenges where you can, this one you XOR with a key of 11, that's base 10. And here, you know the key is a byte between 1 and 40. So you'll have to, like before, make a list of 40 lines, and one of them will become readable. So that's the last couple of challenges in x86 assembly.